don't worry about the odd things. If you don't like them, you don't have to look at them. You only need to look at the good things. But I'm not going to make any restriction here, so a quotient of a subspace can be given by a partial equivalence relation. So the first to note is, just as we had arithmetic combinators, we can find a pairing function on sets of integers there by pairing things by taking a copy of x on the evens and a copy of y on the odds. That pairing function makes the topological space power set cross power set of n homeomorphic to power set of n, and in fact in this notation it's identical to power set of n. Anyway, things like 2 to the n cross 2 to the n is just 2 to the n, but I'm doing it on the T0 topology here. And we can think, therefore, from the pairing subset of n is a binary relation, because every element of power set of n is an ordered pair, and so every subset of power set of n can be thought of as a binary relation. So by a type now, I'm going to understand a quotient of a subspace which could just be wrapped up as one partial equivalence relation. Partial because it's not reflexive over the whole space. The equivalence relation is only concerned with some of the elements of power set of n, but it's a symmetric and transitive relation. That's a partial equivalence relation. This is an old idea in mathematics. Certainly nothing that I invented. It's been used forever. Cauchy sequences for introducing real numbers, say, take convergent sequences of rational numbers and divide them into equivalence classes when you figure out if they have the same limit. So that's taking a quotient of rationals to the n, subspace of rationals to the n. So all kinds of things. When we form free algebras, you have axioms for group theory, and then you take all the words in the group language there, and you say two words are equivalent if applying the axioms for groups, the words can be shown to be equal. That's a quotient of the syntax of all the words in group theory. So the free group is a quotient that way, and so that is used over and over. Use many types of mathematical by taking quotients of certain data constructions, because the data constructions give you many different ways of representing the same element, and you take the quotient in order to say what the interesting partial or total combinatory algebra and added types to them by taking quotients of subsets of the combinatory algebra. So you can do it with Kleene. That's a rather specialized one. There are many other better ones to do than Kleine's first algebra. And now the types form a category because we can say a mapping between two types, these are partial equivalence relations, is defined as the partial equivalence relation on maps to tell you when the two maps are doing the same thing relative to A and B. And what it means is that equivalent inputs give you equivalent outputs here. But notice I'm saying both F and G here because I have to define a binary relation to be a partial equivalence relation. It's a really easy exercise in first order predicate calculus. It doesn't look like a symmetric relation, but it is a symmetric and transitive relation. But you have to do some predicate calculus. When I teach predicate calculus, I usually find the proofs in predicate calculus boring. who cares whether two universal quantifiers commute or not? You just have to read the universal quantifier and you know that two universal quantifiers commute. Why give a formal proof of that? Well, every once in a while you have to really give some formal proofs. So give a proof in predicate calculus that what I've defined there is a symmetric transitive relation. It's a good exercise, and there are a million other exercises here. Using the pairing function on the power set of n, we can define products of types by doing one type on one component and the other type on the other component, and this is much easier to prove is a partial equivalence relation. So we have function spaces and we have types, and you're going to check that this forms a Cartesian closed category, but we can go even further there, and of course isomorphism is necessary to understand what you get out of here. Two types are isomorphic if they're two functions. One undoes the other from maps A to B and B to A, and they're inverse to another. Again, it's a good exercise to prove by this logical definition that isomorphism has the kind of properties you'd expect. And now sums of types means just you indicate indicators, heads or tails here, and you say you do the type on one kind of thing and the other type on the other kind of thing. That's the disjoint sum of two types. And then when we think of properties of isomorphism, these are really good exercises to prove that under isomorphism, products, sums, and function spaces preserve isomorphism. And then you can ask yourself, what is the algebra of types under isomorphism there? And I believe Pepe Longo's student, De Cosmo, but I'm not quite sure, in his thesis proved these are the only laws of isomorphism that you can expect. And of course, it's a little bit like cardinal numbers here. Of course, multiplication, addition are associative under isomorphism, but the more interesting thing is there that a function space taking pairs as values could be reinterpreted as a pair of two functions. These are exercises in functional programming. You take data of one shape, you tear it apart and reassemble it in another shape, and then you prove it's a one-to-one correspondence between them. And so lots of exercise to torture your students with here on these basic definitions. Oh, I didn't mean to do that. Push the wrong thing here. Okay. And subspaces and closures appear as the types very easily there because you can use the identity function on the subspace as a partial equivalence relation. I'm going to have to head a little bit here. Extremely important feature of this model is the scope of the types because it's the whole pair that every countably based topological space is homeomorphic to a subspace of power set of n. And so we're going to get lots of structured types there based on all the kinds product such that equivalent inputs give you equivalent other parameters. That logical definition is a partial equivalence there. Last step here is dependent some, and that just is parameters. Very standard, and so again, now you can cascade this dependency parameters. First, you have a family of types indexed by A, and then you have a family of types indexed by both A and B, but you have to be careful to say how indices from B affect the values there. And then you can have another family indexed by A, B, and C, cascading these things here. Equivalent inputs have to give equivalent equal outputs in these types there. You just have to be careful to say how the dependence works there. So this is a dependent family of types. And now, a big exercise to do is to show if you have this kind of dependence, then if you take the product of sums of products there over many variables like that, you always get a partial equivalence version. This works in any partial combinatorial algebra. You add dependent types to any partial combinatorial algebra. And because the power set of integers is a complete lattice, the power set of partial equivalence relations, I mean the space of partial equivalence relations, we're going up from integers are first order logic, power set of integers is second order logic, types are third order because they're subsets of the power set. So in third order logic there, the types form a complete lattice. So therefore you can ask questions about polymorphism. Are there expressions which have the same type for all combinations of type in this shape here? And here's a simple example that Lambda term has the same type. I mean, has a correct type for any ABs in there. That's polymorphism in types. Moreover, these operations that I'm defining are monotone operators, and in the polymorphic system here, you can think of least fixed points, so you can introduce recursive types, co-inductive types. There are also greatest fixed points, and you can introduce co-inductive types in this model. And so here's a crazy thing that I get to use my name on here. Abadi and Plotkin showed that if we take my numerals, Kleini's lambda calculus arithmetic and the definition doesn't require any work there. So Scott's numerals build the predecessor in, and they can be polymorphic types, as Abadi and Plotkin showed. So lots of fun things to do with these things here. Moreover, we can think of these logical combinations of types giving us logical questions. And so to say for a type that I've established a fact with a type means I have evidence that the type is non-empty. Okay? And now if you think of it that way, then products of types is the same as conjunction. Evidence for a product is saying you can do both P and Q separately somehow, sums either one or the other. Function spaces is the same as implication. It says, if I have evidence for the function space, then if I have evidence for P, it automatically gives me evidence for Q. That's implication there. And the pi's and sigmas correspond to universal and existential quantifiers, because if you look back at the definition of pi and sigma, they're defined with universal and existential quantifiers separately. So when you think of these as establishing that one of those types is non-empty, it's just a statement with a universal quantifier, respectively existential quantifier. I could have introduced equality types there, and so we can write down very formally, say, to say that a binary function is I'll skip over that. I'll skip over that. Can be turned into a model for Martin Lerf's dependent type theory with polymorphic types. So that also brings in John Reynolds and Jean-Yves Girard for polymorphism by just using partial equivalence relations. So there are hundreds of papers, there are hundreds, but there are scores of papers giving you lots of things about types. But I've noticed in those papers that they're heavy going sometimes. So I've tried to simplify things here in two steps. First, to have a simple model for lambda calculus, emphasizing that the definitions of the type structures are just logical. And you're not surprised that product involves conjunction, pi involves universal quantification. So there's no mystery about how you get logical properties out of these things. You have to be a little bit careful with your logic, though, because the number of functions we're using is restricted. You could even restrict just to computable functions and do this. The recursively enumerable sets are closed under application. They have Curry's combinators there. The recursively enumerable sets is a very small model of lambda calculus. And so this is very reminiscent of claiming properties of implication, conjunction, quantifiers there. But what you get is intuitionistic logic, because you don't have enough functions to do the law of the excluded middle. The law of the excluded middle, you have to survey a big thing and find either it's empty or non-empty, and in continuous functions you can't do that. So this modeling of logic via type theory is intuitionistic, and people have written an awful lot about I've now run out of energy, and my batteries are almost exhausted, and I have to say thank you. Thank you. The questioner is. Abbas, a question.
Yes, thank you for that very simple yet elegant and unifying framework. So my question is, your notion of types, does it connect with your notion of ecological spaces?
Oh yeah, it's the same. It's the same.
So
Ecological spaces is just doing the same thing, kind of thing, over set theory there. But instead of having one unified lambda calculus where all functions are the same type, in set theory you have to keep track of domains and ranges of functions there. So it turns out to be the same kind of thing.
So is it fair to say that you started with ecological spaces and then you came up with this model?
No, other way around. I had this model. I had the Cartesian closed version of this model already in '76 in the Data Types as Lattice paper there, but people didn't pay a lot of attention to it. And it was only later, I was very puzzled hearing Per Martin-Lerf lecture many times. Per Martin-Lerf is one of those people that irritate me very profoundly because when he gives a lecture, he never says, he speaks immediately in perfectly formed sentences. Another person who irritated me was Michael Dummett, the famous philosopher. He would get up in a meeting and he would give a sentence with 40 words in it and it would be perfectly grammatical every time. I just hate that. So I was very puzzled by Per Martin-Lerf that when he introduced his type theory, he left off using typed lambda calculus and used untyped lambda calculus formally, but said what all of the expressions, how they should be typed. And I thought, how can you use untyped lambda calculus to explain types? Because I was always used to having typed lambda calculus. But this is an explanation, if you like, of how you can have untyped lambda calculus and plaster the types on top of them. This way, by sorting out behaviors of mappings there. And it's okay to do it on untyped things because the untyped things are very flexible in having many combinators, and so you get good properties out of it just very logically by the properties of the lambda calculus. Other question, please? Somebody must have.
So I have one quite general question. So given, with the development of homotopy type theory, there's been a lot of debate in the foundations community about how valuable that is. You know, what does it do that traditional classical set theoretic foundations don't do for us? And I just wonder whether these sorts of models, whether you think these sorts of models might help resolve some of those questions.
Will have foundational significance here. I'm interested in computational significance, okay? And so typing things is an enormous help for programming languages. And so I'm modeling properties of types that will be appropriate for programming languages here. So I'm really just looking at how you keep sorting out. Want to say, oh, he was able to have this out of types there, where usually we think rather restrictively of a few types at a time here, and this is a whole universe of types. But I'm not thinking foundationally. In terms of foundations. I'm thinking in terms of applications here. All kinds of mathematical structures are available types, and you have a notation for this very expanded Cartesian. I'm thinking of what you can use that for applications. So I'm hoping I might convince Abbas that he could also think of integration and differentiation in a typed system this way, because the Scott domains are contained here in these types there. And so there are lots of things you can define on the Scott domain. The real numbers are one of the types there. The real numbers can be gotten by a partial equivalence relation there. So there are lots of maths to think about in this family of types. Not an okay answer for you? One more question. Please, one more question. Please.
Yes, it is. You were saying that
Wait. Here.
you said that it's much easier to do with Lambda calculus than Turing machines, because with Lambda calculus you can essentially put a function. Programming Turing machines is much harder to program. And you said the only thing that Turing machines might be better at is complexity.
Yes.
Is there any way you can deal with complexity, probably complexity within Lambda calculus context?
I'm sure there's lots, and I haven't developed it because it's not my area of logic here, but when you introduce what corresponds to the universal Turing machine, if I get back to it here, okay, the universal Turing machine can be restricted to finite sets, and so when you do application over a finite set, you only have a finite. But if you say take the universal machine here and restrict to a finite set, then of course the eventual machine is the limit of the finite approximations. So this is a very simple version of space complexity here. And so we can think of what computations can be done with a limitation on space. And so application I give of this is the recursively inseparable sets. If we make this approximations to the computation the following way, we can say the numbers that are lovers of 0 are such that there exists a stage in space for which you achieve a 0 before you achieve a 1. This is Ross's trick for improving Gödel's incompleteness theorem there. And the lovers of 1 are those numbers for which there exists a restriction in space such that you achieve a 1 before you achieve 0. And that is both seen to be a recursively enumerable definitions of two sets, and it's easy to prove those are recursively inseparable sets, just the same way Rosser did for Rosser's idea was to have simple formal arithmetic rather than omega consistency of formal arithmetic in Gödel's original proof. And so by making it symmetric this way, he was able to get by with less. So that's an old idea of recursive function theory, and it gives you inseparable sets. And so this is a little bit of step of understanding space complexity, right? One computation takes less space than another computation. But that doesn't go very far in doing computation. And so one advantage of Turing machines was thinking of the number of steps you go through there, so you can also think in terms of time complexity. Yes? So Turing machine chops things up a little bit more finely, and so you have other complexity assessments to make here. But there's something to do here, and maybe you could also think in terms of how many lookup tables you have to go through, and that would give you some sense of time complexity, but I never tried to work it out. But everything's connected if you just look at it the right way.
I know, I think it's a line of work by Benjamin Wakata and others on the linear substitution calculus, where with certain modifications you can see number of beta steps as a measure of time complexity. Be careful about implications.
Why don't you send me a pointer so that the next time someone asks me that question, I can give your answer, okay? So send me a pointer. I think we should break now. Thanks again, people.